Rewinding a motor from two-phase to three-phase will typically increase its horsepower rating. Here is why. Firstly, increased efficiency. Three-phase motors are generally more efficient than two-phase motors, meaning they can convert more electrical energy into mechanical energy. This increased efficiency leads to a higher horsepower rating. Secondly, better power factor. Three-phase motors have a higher power factor than two-phase motors, which means they use electrical power more effectively. This improved power factor also contributes to a higher horsepower rating. Thirdly, more poles. Three-phase motors typically have more poles than two-phase motors. More poles allow the motor to operate at a lower speed and produce more torque, which results in a higher horsepower rating. Fourthly, increased copper content. Rewinding a motor for three-phase may involve using thicker copper wire in the windings. This increased copper content reduces resistance and improves current flow, leading to a higher horsepower rating. The increased horsepower rating of the three-phase motor may affect the use of the machine in the following ways. Firstly, improved performance. The higher horsepower rating can provide more power to the machine, allowing it to perform more demanding tasks or handle heavier loads. Secondly, overheating concerns. If the machine is not designed to handle the increased power output, it may overheat or experience mechanical issues. Thirdly, speed adjustment. The speed of the machine may need to be recalibrated or adjusted to match the new motor's horsepower rating. It's important to consider the overall design and capabilities of the machine before rewinding the motor. The horsepower rating increase should be within the acceptable operating range for the machine to ensure safe and efficient operation. When dealing with electrical motors and their conversion from two-phase to three-phase, understanding the underlying principles and potential impacts is crucial. A two-phase motor operates using two alternating current sources that are out of phase by 90 degrees, while a three-phase motor utilizes three alternating current sources that are 120 degrees out of phase. This fundamental difference in electrical supply leads to several key advantages for three-phase motors, which directly affect their horsepower rating. Let's delve into the reasons why rewinding a motor from two-phase to three-phase typically results in an increased horsepower rating. The primary factor contributing to the increased horsepower is enhanced efficiency. Three-phase motors are inherently more efficient at converting electrical energy into mechanical work. This efficiency stems from a smoother and more consistent torque production throughout each electrical cycle. In a two-phase system, the torque fluctuates more significantly, leading to energy losses due to vibrations and inefficiencies in the magnetic field generation. Conversely, the three-phase system provides a more balanced and continuous power delivery, minimizing these losses and maximizing the conversion of electrical energy into useful mechanical output. This higher efficiency directly translates to a greater ability to perform work, hence an increased horsepower rating. Another important aspect is the improved power factor in three-phase motors. The power factor represents the ratio of real power used by the motor to the apparent power supplied to it. An ideal power factor is close to 1, indicating that most of the supplied power is being used effectively for work, while a lower power factor implies that a significant portion of the power is wasted as reactive power, which does not contribute to mechanical output. Three-phase motors generally exhibit a higher power factor than two-phase motors due to their balanced and symmetrical construction. This improved power factor means that the three-phase motor can draw more real power from the supply for a given apparent power, resulting in a higher work output and therefore a greater horsepower rating. Furthermore, the design of three-phase motors often incorporates more poles compared to two-phase motors. The number of poles in a motor directly influences its speed and torque characteristics. A motor with more poles will generally operate at a lower speed but produce higher torque. Torque is the rotational force that the motor exerts, and it is directly proportional to the horsepower. By increasing the number of poles during the rewinding process, the motor can generate a higher torque at a given speed, thus increasing its overall horsepower rating. This is particularly beneficial for applications requiring high starting torque or the ability to handle heavy loads. The rewinding process for converting a motor from two-phase to three-phase might also involve using thicker copper wire in the motor windings. The thickness of the copper wire determines its resistance to the flow of electrical current. Thicker wires have lower resistance, allowing for a greater current flow without excessive heat generation. Increased current flow directly enhances the motor's ability to produce a stronger magnetic field, which in turn increases the torque and horsepower. Therefore, using thicker copper wire during the rewinding process contributes to a higher horsepower rating by improving the motor's electrical conductivity and reducing energy losses due to resistance. It's crucial to understand the potential impact of the increased horsepower rating on the machine to which the motor is connected. Firstly, improved performance is an anticipated benefit. The higher horsepower rating allows the machine to handle more demanding tasks and operate with heavier loads without straining the motor. This can lead to increased productivity and efficiency in the machine's operation. However, it is equally important to address potential overheating concerns. If the machine was originally designed to operate with a two-phase motor having a lower horsepower rating, it might not be adequately equipped to dissipate the heat generated by the more powerful three-phase motor. Overheating can lead to premature wear and tear on the motor and other machine components, potentially causing breakdowns and costly repairs. Therefore, it is essential to ensure that the machine's cooling system is sufficient to handle the increased heat load or to implement additional cooling measures if necessary. Another factor to consider is the speed adjustment. The speed of the motor is directly related to its horsepower and torque characteristics. When rewinding the motor, the speed might need to be recalibrated or adjusted to match the new horsepower rating. This might involve changing the gear ratios or pulley sizes in the machine's transmission system to ensure that the machine operates at the desired speed and performance level. Failure to properly adjust the speed can result in inefficient operation, reduced productivity, or even damage to the machine. Before proceeding with the motor rewinding, a comprehensive assessment of the machine's overall design and capabilities is essential. This assessment should consider factors such as the machine's structural integrity, the capacity of its bearings and other mechanical components, and the adequacy of its cooling system. The horsepower rating increase should be carefully selected to fall within the acceptable operating range of the machine, ensuring safe and efficient operation. Exceeding the machine's design limits can lead to catastrophic failures and potentially dangerous situations. In summary, rewinding a motor from two-phase to three-phase typically increases its horsepower rating due to improved efficiency, better power factor, increased number of poles, and potentially increased copper content in the windings. This increased horsepower can enhance the machine's performance and allow it to handle more demanding tasks. However, it is crucial to address potential overheating concerns, ensure proper speed adjustment, and carefully consider the machine's overall design and capabilities to guarantee safe and efficient operation. When evaluating the potential change in horsepower, one must look at the voltage and current changes that may occur. Consider a scenario where 2 horsepower, 230 volts, single-phase motor is being replaced with a 3-phase motor. The full load amps, or FLA, for the single-phase motor may be in the range of 10 amps, whereas the 3-phase motor may have a FLA of 5 amps. The wire size feeding the 2-phase motor may need to be re-evaluated for the 3-phase motor. The overcurrent protection device, like a breaker or fuse, may also need to be changed. The NEC, or National Electrical Code, contains tables that outline the requirements for motor circuits. Specifically, Article 430 covers motors, motor circuits, and controllers. For example, NEC Table 430.248 outlines the full load currents in amps for single-phase alternating current motors. NEC Table 430.250 shows the full load current for 3-phase alternating current motors. Article 430.52 describes the maximum rating or setting for motor branch circuit, short circuit, and ground fault protective devices. This section provides guidance on selecting the appropriate breaker or fuse size to protect the motor and circuit from overcurrent conditions. Article 430.22 covers the size and rating of motor branch circuit conductors. This section specifies the minimum ampacity of the wires feeding the motor, ensuring they can handle the motor's full load current. When installing a 3-phase motor, it is important to understand the concept of phase rotation. A three-phase system, the three phases must be connected in the correct sequence, otherwise the motor may run backwards or not start at all. Phase rotation testers are available to verify the correct sequence before energizing the motor. Another important consideration is the motor enclosure type. Motors are available in various enclosure types, such as open drip-proof, totally enclosed fan-cooled, and explosion-proof. The appropriate enclosure type depends on the environment in which the motor will be operating. For example, an open drip-proof motor is suitable for clean, dry environments, while a totally enclosed fan-cooled motor is better suited for dusty or wet environments. Explosion-proof motors are required in locations where flammable gases or vapors may be present. When selecting a motor, it is also important to consider the motor's service factor. The service factor is a multiplier that indicates the motor's ability to handle occasional overloads. For example, a motor with a service factor of 1.15 can handle a 15% overload for short periods of time without overheating. This is useful for applications where the motor may experience occasional peak loads. In addition to rewinding a two-phase motor to three-phase, it is also possible to convert a motor from one voltage to another. For example, a 230 volts motor can be reconnected to operate on 460 volts, or vice versa. This is typically done by changing the connections of the motor windings. However, it is important to ensure that the motor is properly rated for the new voltage. If the motor is not properly rated, it may overheat or fail. When working with electrical motors, it is always important to follow safe work practices. This includes wearing appropriate personal protective equipment, such as safety glasses and gloves, and energizing the circuit before working on any electrical components. It is also important to be familiar with the NEC and other applicable electrical codes. If you are not comfortable working with electrical equipment, it is best to hire a qualified electrician. Understanding the different types of motor starters is also important for proper motor operation. Motor starters are devices used to control the starting and stopping of electric motors. They also provide overload protection to prevent the motor from overheating. There are several types of motor starters available, including across-the-line starters, reduced voltage starters, and variable frequency drives. Across-the-line starters are the simplest type of motor starter. They connect the motor directly to the power line, providing full voltage to the motor during starting. This type of starter is suitable for small motors that do not draw excessive current during starting. Reduced voltage starters are used to reduce the voltage applied to the motor during starting. This reduces the starting current and minimizes stress on the motor and the electrical system. There are several types of reduced voltage starters, including autotransformer starters, part winding starters, and resistor starters. Variable frequency drives, or VFDs, are the most advanced type of motor starter. They control the speed and torque of the motor by varying the frequency and voltage applied to the motor. VFD can also provide energy savings by reducing the motor's speed when it is not needed to operate at full capacity. When selecting a motor starter, it is important to consider the motor's horsepower rating, voltage, and current requirements, as well as the application in which the motor will be used. It is also important to ensure that the motor starter is properly sized and installed according to the manufacturer's instructions in the NEC. In addition to the electrical aspects of motor installation and operation, it is also important to consider the mechanical aspects. This includes proper motor mounting, alignment, and lubrication. The motor should be securely mounted to a stable surface to prevent vibration and movement. Proper alignment is essential to ensure that the motor shaft is aligned with the driven equipment. Misalignment can cause excessive wear and tear on the motor bearings and the driven equipment. Motors also require regular lubrication to prevent friction and wear. The type of lubricant and the frequency of lubrication depend on the motor's design and the operating conditions. It is important to follow the manufacturer's recommendations for lubrication. By understanding the electrical and mechanical aspects of motor installation and operation, you can ensure that your motors operate safely and efficiently for many years. Another important factor to consider when dealing with motor rewinding and conversions is the potential impact on the motor's efficiency. While rewinding a motor from 2-phase to 3-phase can increase its horsepower rating, it can also affect its efficiency if not done properly. The efficiency of an electric motor is the ratio of the mechanical power output to the electrical power input. A higher efficiency means that the motor converts more of the electrical energy into useful work, while a lower efficiency means that more energy is wasted as heat. Motor efficiency is affected by several factors, including the motor's design, the materials used in its construction, and the operating conditions. When rewinding a motor, it is important to use high-quality materials and follow proper procedures to minimize any negative impact on efficiency. In some cases, rewinding a motor could actually improve its efficiency if the original windings were damaged or inefficient. However, if the rewinding is not done properly, it can reduce the motor's efficiency, leading to increased energy consumption and higher operating costs. When converting a motor from 2-phase to 3-phase, it is also important to consider the impact on the motor's power factor. As mentioned earlier, the power factor is a measure of how effectively the motor uses electrical power. A low power factor can result in increased energy consumption and higher utility bills. Converting a motor from 2-phase to 3-phase can improve its power factor, but it is important to ensure that the motor is properly matched to the load to maximize the benefits. Another important consideration is the motor's insulation system. The insulation system protects the motor windings from electrical shorts and ground faults. When rewinding a motor, it is important to use high-quality insulation materials that are compatible with the motor's operating temperature and voltage. A damaged or degraded insulation system can lead to premature motor failure and potentially dangerous electrical hazards. It is also important to properly test the motor's insulation resistance after rewinding to ensure that it meets the required standards. In addition to the technical aspects of motor rewinding and conversions, it is also important to consider the economic aspects. Rewinding a motor can be a cost-effective alternative to replacing it, especially for large or specialized motors. However, it is important to carefully evaluate the cost of rewinding versus the cost of replacement, taking into account factors such as the motor's age, condition, and efficiency. It is also important to consider the downtime associated with rewinding, as this can impact production and increase costs. When evaluating the cost of rewinding, it is important to obtain quotes from reputable motor repair shops and compare their prices and services. It is also important to ask about their experience and qualifications, as well as their warranty policy. A reputable motor repair shop will be able to provide you with a detailed assessment of the motor's condition and recommend the most cost-effective solution. In summary, rewinding a motor from 2-phase to 3-phase can be a complex process that requires careful planning and execution. It is important to consider the technical, economic, and safety aspects of the conversion to ensure that it is done properly and that the motor operates safely and efficiently. By following proper procedures and using high-quality materials, you can maximize the benefits of motor rewinding and conversions and minimize any potential risks.